Regular portals look like flat doorways. Those are pretty straightforward. So a lot of people in the comments asked, what if you made a sphere-shaped portal? It turns out such a portal explains some properties of recursive space, which is often found in pop culture. We will look at its geometry and at the physics of objects in this kind of space. For example, what happens if you collide with yourself? And along the way, we will also talk about recursive gravity. One important clarification: wormholes are the topic of the next video, but this one is specifically about what happens if you make a portal shaped like a sphere. So let's figure out how this works so you can understand what this video is actually about. First, let's see how teleportation works in 2D using light rays as an example. We have two flat portals and a light ray. When it crosses the surface of the blue portal, it comes out of the orange one. Same thing if the portal's surface is a semicircle. The ray of light enters the inner side of the blue semicircle and exits from the outer side of the orange one. In both cases, the ray ends up in exactly the same place. I call this property the axiom of surface irrelevance. Essentially, that's my definition of what a portal is. Also, according to this axiom, the boundaries of the portal are fixed. They cannot be moved, but the entire surface between them can move freely. Now let's apply the same logic to spherical portals, which have no boundary at all. And yes, for the sake of generality, I will be calling 2D circles spheres as well. So the ray goes into the portal, enters from the outside, and in the other portal comes out from the inside, and then vice versa. Now let's look at this in 3D, using the exact same logic. Here are two spherical portals. One teleports to the other. We turn on light teleportation and... wait, there is nothing to see. Where are the portals? Well, the truth is, portals like this don't do anything. The reason is that after passing through both portals, the ray arrives exactly where it would have arrived without them, which is why nothing happens. And by the axiom of surface irrelevance, the portal can have any shape at all, as long as it's closed, since it has no boundary, which means its surface can even be zero. It's a portal made of pure surface after all. This doesn't work for regular portals though, because they are not closed. For the case with an ordinary portal, light rays act differently than in the case without portals. Then what is this whole video about, you might ask? This video is about the case where you can't collapse the portal into nothing, when one portal is inside the other. This will demonstrate how we can simulate a space that repeats infinitely in both smaller and larger directions. But before that, a quick word from the sponsor that makes videos like this possible, the Opera browser. While making animations for this video, I needed my own renderer next to the reference material. In Opera, I just drag a tab down and the screen splits. Article on one side, my demo on the other. And I can even add more panes, up to 4 tabs at once, in vertical, horizontal or grid layouts. No window juggling. Recently I found a 20-minute video and asked Opera AI to summarize it, just to check whether it has anything new to say compared to every other video on this topic. It does, by the way, and I liked it. Opera AI needs no extensions, not even an account, and it's completely free. And when a video is worth watching while I do something else, I pop it straight out of YouTube. It floats anywhere, even outside the browser. Later in this video you will see 2 animations that took me 8 hours to make. For work sessions like that, there's also a detachable music player that supports 7 streaming services, from Spotify to Tidal, and it auto-pauses whenever a video plays. If any of this sounds useful, download Opera with my link in the description. Next we will be looking at pretty weird concept: scaling portals. This is when one portal is smaller than the other, meaning they can change the scale of objects. This is pure mathematical speculation. Nothing in the physical world can rescale objects like that. To make a portal a scaling one, You mathematically shrink one of its two parts. Then we place the small blue sphere inside the orange one. When we turn on light teleportation, it looks like nothing happened. But if we fly inside this construction, we see our own back. And yes, a reminder, I visualized the camera with this camera module. And here a single camera is repeating infinitely. But why do we see exactly this? First, let's understand how light behaves on the outside. When it enters the orange sphere from the outside, it exits from the blue one, and then back again. And this doesn't depend on the relative position of the spheres. The light always arrives at the same place. So if a camera is placed here, it won't notice any difference between the portals being there or not. Okay, now let's shine a ray on the inside. It enters the orange sphere and exits the blue one within the same enclosed space. But now it is scaled down. If a camera is standing here, it will see the object that emitted this light as something very tiny. And now the behavior does depend on the relative position of the spheres. Because if we move the blue sphere, the tiny object ends up somewhere else. Let's go back to 3D. As a reminder, we are located between two portal spheres. And I am adding this object here. After turning on light teleportation, we see that it repeats, getting smaller in one direction and larger in the other. Just like we do actually. And everything here is black, because there is nothing else, besides the object and us. Absolutely no access to the outside world. So what is this repeating space we've ended up with? Remember, in this video I showed that if you place a small semicircular portal inside a big semicircular one, you get a pocket dimension. But what if we close that portal while leaving the teleporting surface in place? Then from the outside we'll see the portal disappear, leaving empty space in its place. And from the inside we'll see the window to the outside world close. But the portal surfaces remain, with one inside the other. In other words, what's left is a pure pocket dimension with no way to get in. And that's exactly what the small sphere inside the big one is doing. This pocket dimension works the same way whether it's this shape, or made of cubes, or made of spheres. But I'll stick with spheres, since they are simpler and symmetric. Further on, for 2D, I will show what the teleportation of light through portals would look like from inside the two-dimensional space. We could always do without it, but it's more fun this way. Let's figure out why in a pocket dimension made of spheres we see repeating copies of the same object. Suppose we illuminate an object and a ray bounces off it in this direction. Then it teleports through the portal once and reaches the camera. To the camera, this looks like there's a small version of the object in that direction. If the reflected ray goes in this direction, it teleports twice. And to the camera, it looks like an even smaller object. And finally, if the ray goes in this direction, the camera sees it as a large object. Recursive space emerges naturally when light rays simply teleport through our spherical portals. And here's a beautiful little animation showing what happens if you rotate one sphere relative to the other. And here's what it looks like in 3D. You can see that the smallest and the largest objects rotate the fastest. These spheres can be rotated and even moved around. But what if you want to take the small one outside of the big one? Portal surfaces cannot intersect. They must be teleported. Remember how in this video I solved this by stretching the teleporting surface so that nothing intersects? Here we can also stretch the surface in the place where the small sphere enters. But because of that extension, the surface of the blue one starts sticking out again. We stretch the orange one once more, and now we can stop. This is complicated, but at least we don't have to teleport portals through themselves. Still, these arbitrary shapes aren't very convenient either. And there is an even simpler way. We just increase the radius of both spheres while preserving the proportions. And that's it. So for any position of the spherical portals, you can find a radius multiplier that keeps these spheres from intersecting. And here is the next interesting scene in 3D. Here the rotation angle of one sphere relative to the other is exactly the golden angle, a bit over 137 degrees, which produces this absolutely gorgeous fractal. Plans use this angle and it is connected to the Fibonacci sequence. It is a beautiful scene, and you are probably wondering how I arrange the spheres to render it. The distance between the spheres is just 4 meters, while their radii are about 140 and 141 kilometers respectively. Those spheres are far too big to display or to work with at all. So I rendered this with an alternative method based on coordinate systems. I'd love to tell you about it, but the video is getting too long, so maybe some other time. By the way, you can always play around with this scene in my web demo via this link in the description. This fractal probably inspired you, and someone is already wondering how to make it even more beautiful and interesting. Unfortunately, if you take two pairs of spherical portals, no amount of nesting the spheres inside one another will create a double pocket dimension. And now physics. There is a legendary video on YouTube about a game inside a game inside a game. It has a scene where a cube falls onto a smaller version of itself. Obviously, the same mechanism that drives spherical portals is at work here. And since I have a physics engine, I can simulate this. Unfortunately, what I am about to show are preliminary results, since I still can't formulate a proper physical theory of scaling portals, especially when it comes to inertial mass. In this model, inertial mass doesn't change after teleportation, even though the body has shrunk by a factor of 2. So take all this with a grain of salt. Alright, let's take this scene. We have two spherical portals. We have an object, and its initial velocity points this way. If we turn on light teleportation, we see that it is flying straight at itself. When the collision happens, I gradually slow down the simulation. The infinite stack of further layers presses on the lower ones harder and harder. Because of this, the object can't bounce back or slow down. It gets squashed even more, and eventually everything shatters to pieces, because my physics engine just can't handle it. And without the slow motion, all of this happens in the blink of an eye. There is another collision scenario, where the velocity points like this. That is, the object flies at an angle. In that case, it survives. I also found this configuration. Here too, the object flies into itself at an angle. Everything compresses dangerously, but in the end it bounces off and the object stays alive. And if you want to play with this physics yourself, it runs in real time in my program OptoLab, which is available on my Patreon at every tier starting from $1. And to wrap up, I'll explain how gravity works in this system. If we take two portal spheres and place this circular mass between them, then its gravity looks like this. It remains unchanged if you scale the radii of the spheres in the same proportion, which obeys the axiom of portal surface irrelevance. And here is what it looks like if we teleport the light. The large and small images have exactly the same mass as the original object. This is highly counterintuitive, but my finite element method outputs this solution right out of the box. And I haven't found any contradictions in it yet. But to make this kind of gravity work, we need to solve a lot of problems, which I will talk about next. The first problem is that the space is closed, which means gravity isn't constrained by boundary conditions. And if we just run the solver as is, it will grow infinitely and diverge. I already discussed this problem in my previous video, where I calculated gravity on a torus. And there we concluded that we need to calculate the area of the torus, then all the mass on it, and then add a uniform negative mass at every point, so the total net mass equals 0. Let's try the same thing here. The area between the spheres equals p big R squared minus p small r squared. And there's one problem with it. If you rescale the sphere radii while keeping their ratio, this area changes. Alright, I'll go ahead and place the negative mass between the spheres based on this area anyway. And we get this solution. I change the radii and yep, the gravity changes. That violates our axiom, which means we are doing something wrong. The negative mass needs to be placed some other way. While solving this problem, I discovered one more interesting property of a spherical portal inside a portal. This point here, where everything in this system converges, is the fixed point of teleportation operation. That is the point that stays in place under teleportation. And it turns out that if you place the centers of the spheres at this fixed point, you get exactly the same recursive space as with the previous arrangement. In other words, the space formed by this arrangement of spheres and by this arrangement of spheres are equivalent. This time the center of both spheres is located at the same point, which gives us more symmetry and room to maneuver. In this arrangement, solving the problem becomes much easier. First, note that the distance between identical masses, while not constant, gets multiplied by the same factor each time. So we need to place the negative mass so that it changes gradually from one mass to the next, stays symmetric, and grows along with this distance and scale. I will reveal the trick right away. Initially, we are using Cartesian coordinates x and y. We need to switch to polar coordinates, where the horizontal axis is the angle of rotation around the center, and the vertical axis is the distance to the center. You can see the picture starts repeating horizontally, precisely because polar coordinates wrap around in a circle. There is nothing below, because distance can't be negative. Next, we know that the distance between each sphere changes in a geometric progression, and this is where the logarithm function becomes extremely useful. It can turn multiplication into addition, which means the geometric progression turns into an arithmetic one. We apply the logarithm and see how these small spheres go infinitely far down, while the top one become normal sized instead of stretched out. We end up with a very evenly spaced grid that will be convenient to work from here on. I spent about 8 hours on these two animations. I think that deserves a like. By the way, exactly the same coordinate transformations were used in the recent 3 Blue 1 Brown video about the Escher painting. I highly recommend watching it. And this already looks a lot like a flat torus from the previous video. But is it really what we need? As a first experiment, I changed the sphere radii, and as we remember, the area changes with them. But in log polar coordinates, it just looks like a simple shift that preserves both distance and area, all thanks to that same logarithm turning multiplication into addition. So if we lay out uniform negative mass in these coordinates, it will always be the same regardless of the sphere's sizes. We place it uniformly here and then return to Cartesian coordinates. As for how this is implemented, every point gets an area density, equal to 1 divided by the squared distance to the fixed point. And when we compute a triangle's area to decide how much mass to put on it, we have to multiply it by this density. After that, we run the gravity computation with the new negative mass, and the solution converges. And for different radii, it remains the same. Finally, gravity is solved now. By the way, look at the direction of gravity. It is directed as if it goes around other sources of mass. That looks pretty strange in Cartesian coordinates, but in log polar coordinates, gravity just heads straight toward the mass. Now let's experiment a little. In the previous video, I showed the concept of self-force. That's when an object's own gravity pulls it somewhere because of how the space around it is curved. And there I showed that on a regular torus there is no self-force. But here the self-force pushes any body away from the fixed point. And if we run an actual simulation with an initially stationary body, you can see it trying to fly farther and farther from the center. Also, the cell force almost doesn't depend on the relative rotation of the portals. The arrow still points away from the center. It turns out that in a space like this, everything will strive towards infinite separation and expansion. Under the last video, a lot of people commented that the cell force of certain portals looks a lot like dark energy and the expansion of the universe. But this specific example of self-force looks the most like dark energy. Maybe we live on a surface of a four-dimensional sphere, sitting in a space like this, constantly stretching and expanding. Now for a bit of history and my future plans. I made the first version of this video back in the summer of 2025, but never released it since I decided to focus on the gravity video instead. And that's when it became clear that I really lacked tools for visualizing 2D portals. So I decided to try the well-known Manim community, based on 3Blue1Brown's library. I managed to program some animations, but I quickly got frustrated. Every change has to be run through the console, and it takes quite a while to render. And if I wanted to nudge something, I had to change numbers in the code and rerun the console command just to see the result. Meanwhile, in my Portal Explorer, every change shows up instantly and runs on interactive sliders. And at the time, I couldn't find a way to get interactive sliders like that in Manim. So I decided to try writing this in Rust, using the IGUI UI library. I did it in the most naive way possible, recomputing every ray from scratch on every frame. And it computed instantly, even with 1,000 rays teleporting through portals. After that, I decided I'd build my own Manim in Rust with a visual editor just like in Portal Explorer. That's how OptoLab was born, the program behind the animations in my last 3 videos. A few videos from now, I'll release it as open source. For now, there's an online version of this program, without any of the Portal stuff, but focused on shaders. If you use Shader Toy, but wish it had interactive sliders and more control, this program is for you. You can create separate texture components, write to multiple textures at once. Everything is parameterized and so on. The program has documentation that I wrote myself by hand. You can read more in my public Patreon post. The program itself is at this link, currently in preview mode. I am making this announcement to gather early feedback and find out whether anyone actually needs this program at all. So if you'd like to port your shader to it, message me on my Discord in the OptoLab channel. I plan to polish it up and make a separate video about it. This program will be something in between Shader Toy, Manim, and my Portal Explorer. And that's all from me. Huge thanks to everyone supporting me on Patreon and Boosty. Thanks for watching and see you soon!